My name is Burk Hufnagel. This is Beyond Test-Driven Development, and before we get started with that, I want to show you something interesting, or at least I hope you'll find it interesting. Amazing, right? This is a wireframe cube. It's called a Necker cube. The difference is that there's no clues here as to which sections are in front or behind, right? So if you look at that upper right square and kind of focus on that, your brain might take a sec, but you should see it as being the one closest to you. Can you see that? Yeah? Okay, focus on the lower left one and see if it switches, right? That's working? Okay, cool. Your brain's doing what it's supposed to do. This is the easy one. We're going to go to a little more complex now. Here, we've got some black circles, and now we've got a white Necker cube sitting on top of these black circles, right? Can you see it? Can you make the two squares pop in front? Yes? Okay, cool. Now, this is where it gets really weird. Imagine that this white area is a surface, and those black circles are holes. You're looking through that surface, and behind it, there's another black surface, but there's a cube. But there's a cube floating in between, right? So you've got the white and the black and the cube in between. Can you see through the holes and see the cube kind of hovering behind it? Who sees that? Okay, this is really, really cool because there's no circles, there's no cube. It's just some little sections of circles arranged in a way to suggest that there could be something there. Your brain is doing what you're telling it to do. You're saying, hey, I want to see a square. I want to see that cube behind the surface. I want to see it in front of the surface. And your brain is taking the same exact information and changing things so that you believe what your eyes are seeing is actually a cube in front or behind, and which surface is closest, right? The data itself is exactly the same. It's how you're interpreting it. And for many of us, there's a lot of ways this happens during life, right? If you look at something from a particular view, it's obvious that this is what's going on. There's a cube behind this white surface, right? But if you change your point of view, you can see something different. The real truth hasn't changed any, but the way you interpret it makes it easier or harder to see things, okay? And we'll see more of how that works with this. So, this is the start of the adventure. My name is Burk Hufnagel. I'm a software architect and a programmer with Doherty Business Solutions. We're a consulting company based out of Atlanta, but we've got offices around the country, and that's all good stuff. I've been doing this for a long time. If any of you know Sun Microsystems, they're the guys that originally created Java, and I got certified with them, and got to help with this book. They gave me a great quote. Kathy and Bert were the authors of the exam. They wrote a book on how to take the exam, and then they gave me props for fixing their code. So I was like, oh yeah, I'm putting that on my resume. You know. So I've also been involved with Java a lot. I'm a Java champion. I got recognized as a Java rockstar, which basically means I was one of the top 20 talks at the Java 1 conference, which has like 100 and something talks going on. So that was really cool. And I got to contribute to these. I don't know if you've seen these books before, the 97 Things book. O'Reilly tried an experiment. These are essentially open source books. None of the articles that are in there are copyrighted. So you can take them, use them, do whatever you want to do. There's somebody on Amazon actually has one of these books under their own publishing heading, right? It's the same exact content, but because it's not copyrighted, they're allowed to do that. So it's kind of cool. So that's me. So what is TDD? How many people here are actually doing test-driven development currently? Okay, cool. How many people here have tried and maybe do some? Okay, good. So just to make sure we're all on the same point, we'll take a quick look at what TDD is. And TDD actually started a long time ago. I don't know if any of you guys recognize this. But during the Mercury space mission, whose job was, the goal was to put a person in orbit and bring him back to Earth safely, right? So this is the late 1950s, 58, 59. They were actually doing a form of test-driven development. Now back then, you didn't have computers like we have now. You had the big, huge mainframes, and you had punched cards and magnetic tape and stuff. And they would actually take punch cards and create the expected result punch it into the card, run the programs, compare the cards, and see if they matched or not. And that was how they did test-driven development back then. It's how they proved that the program did what it was supposed to do. For most people, though, this book is the introduction. Kent Beck put this out in, I think it was 2002. And it describes, it's what most people use as the foundation for test-driven development. So the key point on this was you have what I call an efficient three-step process. And it's efficient because there's no wasted space, there's no wasted time. And it's 3 steps, so it's pretty easy to think about, but to actually do can be challenging. First step is you're going to write a fading automated test. Now, an automated test means that the computer has to decide whether it passed or failed. If you write a test, and at the end of it, you just spit out a bunch of data, and some human has to look at it and go, yes, that passed. It is not an automated test, okay? It's getting there, but you need to actually have the program decide. This step is called red because when they first started writing the tools to run this stuff, if there was an error, they would show it to you in red. So this step became known as red. The next step is to write just enough production code to make it pass, right? That's called green because if it passes, you get your information in green. And the third step is refactoring. You guys are all familiar with the idea of refactoring? Okay, just basically cleaning up the mess you made in the first 2 steps, right? Trying to make things easier to understand, getting rid of duplication, that kind of thing. Refactor doesn't get a cool color name because when you're refactoring, you shouldn't change how it behaves, so it should stay green. And calling it red, green, green didn't make sense, so they call it red, green, refactor. Okay, so why should you care about any of this stuff? Well, if you listen to what the people who do TDD say, you get all sorts of cool benefits, right? You have fewer bugs in your code. And the bugs that you do have, you get fixed easier, so you spend less time debugging. Now, I don't know about you, but that's a good idea for me. Debugging is not my favorite thing to do. Once in a while, it's a cool challenge, but I have better ways to spend my time than that. Because of this, you deliver to production faster, right? If you have fewer bugs, then when you go to QA or UAT, it's less likely they'll find anything, which means you don't have that big loop of writing some stuff, giving to somebody, having them come back in a couple of days and say, oh, I found an issue. I got to fix that, right? If you can cut one of those loops out, you've saved days. Okay, higher code quality. This is another claim, and it's based on fact because when you're writing the tests, well, we've got 2 types of quality we talk about, but we'll get into more detail on that in a sec. But you do wind up having higher quality code, which means it's easier for people to maintain, it's easier for the business to make use of it. So that's the first piece. Okay, so why is adopting it so hard, right? It's a simple 3-step process. First thing is, if it sounds too good to be true, it probably is, right? It's like, people say there's no such thing as a free lunch, or things like that. We tend to be suspicious. It's like, okay, this is really great, but how does that work? And I think of it as like this. If you're working on a project, you're probably already working more than 40 hours a week. You're probably doing some overtime because it tends to get that way. And what we're saying here with TDD is if you add some more stuff, well, you'd think it would happen like this. You'd have more hours to work, right? But we're saying with TDD, no. It goes the other way. And that's intuitive, right? It's like, wait, if I'm doing more things, how am I getting done faster? And the key to this is programming. Programming isn't just programming, right? We do multiple things in there. We're doing design, we're doing manual testing, there's debugging, and of course writing code. And so what happens here is TDD is not a bolt-on extra thing that you do. TDD flavors everything that you're doing because it's a process. It's how you do things, right? So if you've ever learned arts or anything like that, there are more efficient ways of doing things and there are less efficient ways of doing things. And TDD helps you be more efficient at this. And so what happens is you're still doing those kind of things, but the percentages change, right? And I can make these slides available for you guys, a PDF or something, so you don't have to worry about that. But so what happens is you spend more time doing design, you spend less time doing the testing and coding. So that test debug in the upper right there, that's those 2 chunks down there at the bottom, the manual testing and debugging. You spend a lot less time with that. People will tell you after doing this, you kind of forget all the cool keys, the shortcuts for using your debugger because you don't use it nearly as much. You spend more time coding, which for programmers, I hope is a good thing. Right? That's the key piece. And if you enjoy it, you spend a little more time programming and you get a lot less time having to do the other things. So this is kind of how it works. And then because of this, you can actually start adding some new stuff. You can take on another feature, or maybe you can start looking at other possible tools, that kind of thing. But there's space to do more than what you're currently doing. Once again, it seems a little counterintuitive, but if you can be more efficient in how you produce the code and produce less bugs to start with, then you wind up with something like this. So that's a too good to be true piece. People have a couple of main complaints. They say, gosh, we don't have time to do this automated testing stuff. It takes too long. Okay, what that means is you don't have time to do all the manual testing that you're doing either, because manual testing takes longer and is less accurate than automated testing. Right? It takes you a couple of minutes to write a test. When you run it, it takes fractions of a second generally. Right? So if you don't have time to do that, you've got other problems. And then our code is too complex to test. The results is just, okay, so you have a person testing this? If you can't describe to a computer how to know whether it's right, how does the person know whether it's right? Now, if what you're doing is generating artwork, right, paintings or poetry or something like that, maybe that's something a person has to get involved with. But if you're doing business things, totaling up taxes or counting inventory, that's something a computer can handle. It doesn't really matter how complex your system is. The results are going to be something simple. If they're not, a person's not going to be able to tell if it's working either. Right? So for me, those two are actually, they're another way of saying this. We don't trust automated testing because this guy had a great quote. Edsger Dijkstra, I think is how it's pronounced. Edsger Dijkstra. Has done a lot of stuff. Look him up. He's contributed a lot to computing. But he had a great quote. He says, if debugging is the process of removing bugs from our code, right, then programming must be the process of putting them in. Right? On some level, I think we all understand that the bugs in our code are because we made mistakes. We put them in there accidentally. We misunderstood a requirement, perhaps, and put in the right code to do what we thought it was supposed to do, but it turned out to be the wrong thing. Or you meant to do greater than or equal to, but you got greater than and forgot the equal to because somebody called your name, and right? So we make little mistakes. And test code is code. So if I can have bugs in my program, why can't I have bugs in my test code? And if I have bugs in my test code, how do I know it works? Right? It's a real big difficulty. TDD addresses that problem. Through the odd idea of writing tests first, and we'll get into that whole thing. But so this is the thing. It's true, yes, programming is where we put the bugs in, but that's okay, because we have ways of taking care of that. So we take care of those two things. And the last part is writing tests first is crazy, right? It's like, we don't do that. You do something, then you test it. You don't test something and then do it. It's like you're walking into class on the first day and, okay, here's the final exam. What? No, it doesn't work that way. First you do something, then you test it. And that makes sense too. But if test first is crazy, then what would you do? Test last, right? You write the code, then you write a test for it. That's got a problem. Actually, there's a couple of ways you can do this, and both of them have an issue. First is, write the production code, then write the test for it. Okay, that sounds very reasonable, right? But you got a problem. You don't know either one of those or both could have a bug, right? Because you just wrote the code, it's probably correct, but we know from our past behaviors and past history that sometimes we introduce bugs into things. So if there's a bug in the test code, maybe it's going to pass all the time, or maybe it's going to fail all the time, right? So when you run it, you don't know if it passed. Did it pass because it's correct, or did it pass because I've got a bug in the test program, so it's always going to pass? So then you have to try and break the production code and see if the test fails, or it's a mess. You don't have a stable place. You have a question? Okay. Cool. Do they talk back?
Sometimes, and that's very.
Okay. Question. If you have the normal number of fingers and thumbs, how high can you count? And not high like this, but how high can you count on your hands? 10? No. If you're an old-style programmer, you can count to 1023. Binary. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, right? So it's how I got sucked into programming. Anyways, back to this. You got a problem because either one can have a bug, and so you can't trust either one of those. There's no way to verify until you break out the debugger and do all the manual testing. So that doesn't really help a lot. The other way of doing this is, if you write and debug the program, right, and make sure that the program works, then you write the test, then you can make sure that it's working properly. The problem with that is, okay, you take an hour and you write some code. You take another half hour and you debug it, right? Everything is clean, beautiful. You know that that program works. You start to write the test and your brain says, hey, what are we doing this for? We know it works, right? There's no immediate value for you in this process. 6 months from now, if you have the test, that'll be a good thing. Or if you hand this off to somebody else, it's great that you have the test. But in the immediate moment, right, your brain is saying, hey, we could be working on another feature, we could fix another bug, we could go home like everybody else did 2 hours ago. This has no value right here. Right? So it's very hard, and that's why tests last. If you look at places that say they do test last, there's not a lot of tests there. Because if you do the way that works, then you have to fight yourself to make yourself write that test. And it's very frustrating. Okay, so we'll talk about test first some more in a bit. So that's that part. Okay, so that gets us to the next part, the good part, going beyond test-driven development. Okay, and we'll be covering these pieces. Specs is not eyeglasses. Specs is short for specifications, but it doesn't fit on the screen, so we'll get into this. Quick reminder, right? The whole idea of test-driven development, 3 steps: write the test, make it work, clean up your mess. Okay, so benefits of writing the test first. If you're going to write a test, you have to know what the foundation is, right? So your requirements are going to tell you, this is what the system should do. Okay, and if you're going to write a test for it, then you have to have very clear requirements, right? It can't just say, make this work or whatever. If you've got an ATM, right, it's going to say, okay, when a customer gives us valid credentials, they should have access to their account. You say, great. What happens if we don't have valid credentials? They should give them another chance, right? Put the card in, do the PIN, whatever the credentials are, retina scan. If it works, great. If it doesn't work, tell them no, try again. How many times? You just let them keep going until, or do we stop? So it gives you a way to get clearer requirements from the business, because as you're thinking about what test to write, your brain's automatically going to come up with other possibilities, right? So we have that. If you write the test first, you're actually doing design, right? So, because as you write the test, you say, okay, I want to create an instance of, I need a class. We'll call it credentials verifier. Okay, cool. So I'm designing that. I'm designing because I'm saying, here's a class that I need. Here's the methods I need in that class. Here's the parameters I want to pass into that method, right? And here's what I expect to come back. That's all design work, right? It's because you're not implementing it at this point, you're just referencing it, you're doing the design, and which means you're decoupling your design from your implementation, which if you've taken classes on object-oriented programming and all, they'll tell you that's one of the things you're supposed to do, is decouple the implementation from the design. So this is a way of doing that. And the last thing is, when the test passes, you know the code works, and you know the test works, right? Because before you wrote that code to make it pass, the test was failing, and it was failing for a particular reason. They don't mention that here, but you want to make sure that the test is failing because I'm not getting the expected result, which means the system is not behaving as I expect it to. So that's that. Okay, now we said that writing tests first increases quality. We got 2 things, right? First is meeting the business requirements. Because you're writing the tests and you have to get that clear understanding of what the business requirements are, you're going to go through each one of the requirements, and so you're much less likely to deliver something that you thought had all the requirements met but doesn't, right? So that's the first piece. And of course, that means that you're turning in all of the business valuable code, all the features that they want on time, or possibly early. The other piece is, because you're refactoring, you have a chance to create code that's easy to understand, easy to modify, which means somebody else can do it and you don't have to, right? If you're the only one who can work on your code, then you can't do anything else. You have to be there to maintain that and all, right? Joe's the only guy who understands it, so we have to do this, right? And then they hope that Joe doesn't go away because no one else understands how it works. Okay, so problems with tests first. How do you write tests for code that doesn't work, right? We started talking about this, and I told you we'd go into that. Here's the time. The other thing is, right, how do you know what test to write, and how do you know when you're done? Right? Those are the three biggest issues people have when they're doing test-driven development, and when they first get into it. And this is a chance to do something that we did earlier. Remember this? Switching between one thing and another? We're going to change our focus. Instead of talking about tests for a second, we're going to talk about specifications. A specification is a description of something that doesn't exist yet. So if you want to buy a house, you say, okay, I want a two-story with full basement, all these kind of things. You're specifying what you want to have, right? And it makes sense to do it because the thing doesn't exist yet. So you're telling them what do you want. So we're going to change test to specification and see what this says. Okay, so writing specifications first. How do you write a specification for code that doesn't exist? Well, that seems reasonable. Since specifications describe something that doesn't exist yet, that seems very doable, right? We're just going to say, this is what I want to have happen. Given this setup, when this occurs, then this should happen, right? You guys are familiar with the given, when, then storyline stuff? Yeah. Okay, good. How do you know what specifications to write? Easy. The requirements tell us, right? Here's the requirements. For each requirement, you come up with the different scenarios. What happens when they give us good credentials? What happens when they give us bad credentials? And we work all the way through. And once we've got our specifications written, we know we're done. So we know how to write specifications. We know which ones we need to write, and we know when we're done, when all the requirements are met. So that sounds really easy, right? Way better than dealing with that whole testing. The problem is we think about test and we think of this is how it has to be, but it doesn't, because with specifications, right? Yeah, once again, based on requirements, describe what should happen, no guessing, and separate the implementation. We talked about all that. But we don't stop with just that piece, because what we want to do is we want to have what are called executable specifications. And this is where we take the text, the descriptions, and marry that with code, right? So if you've used something like, any of the test frameworks, right? They'll have a place where there's something like describe and then a string. If you put your specifications in there, right, then you get this cool thing called an executable specification. Right. They can generate living documentation. We'll show you how that works when we look at the results, the reports. And it bridges the gap, right? So specifications are about design, tests are about implementation, and this is going to bridge the gap between the two of those, and you'll see how in just a sec, right? Basically, the idea is if we're looking at it in one way, we see a specification, and we look at it the other way, we can run it like a test. That's the goal. More information, right? Tests, oh yeah, if you've seen people who write tests, a lot of times you get something like the name of the test is test my function, right? Or test function name, or something like that, which doesn't really tell you a whole lot about it. And then in the test, you just see it do a bunch of stuff, and if it fails, you know that test function failed, but it doesn't give you a clue, right? Because it's written for the guy who knows what the system is supposed to do. It's written by the person who just wrote the code, so you know what it's supposed to do. In your head, you've got all the context to understand what that does. But if you come back to it 6 months later, or if somebody else comes back to it, they don't have that context. And so what they see is, I got a test called, test my function, and it's not working. Okay, what does that mean? I don't know. I don't know what my function does. Okay. So, you guys familiar with FizzBuzz? FizzBuzz is a game, right? So you're going to count from 1 to 100. Display fizz when the numbers are evenly divisible by 3. buzz when they're evenly divisible by 5, and fizzbuzz when it's both 3 and 5. Otherwise, you return the number. And so you get something like this: 1, 2, fizz, 4, buzz, fizz, right? So it's a fun game that kids play. And programmers decided, oh, this could be a neat little challenge for programmers. So a test might look like this, right? Describe fizzbuzz. It executes, and then you've got your different expects. It's a little hard. This is actually taken from the GitHub repository. So I don't know why he cuts the line shorts and wraps so much. So if you clean it up a little bit, you can see kind of what's happening here. So we got 1 to 1, 1 and 2, and 1, 2. So the left side is the inputs, the right side is the outputs. It doesn't really tell you. If you're not familiar with fizzbuzz, looking at this doesn't tell you anything at all about what fizzbuzz is supposed to do. You can start guessing, but there's nothing really there. Come on. Okay, and if it fails, right, so let's go back a sec. Okay, so we got the name fizzbuzz, which doesn't tell us anything. We got it executes. Okay, it's code, it should execute. But once again, it doesn't tell us anything useful here. The other piece was, you got all these expects, right? So you know it's supposed to do, these are things that should happen. The problem is that if one of those expects fails, and we'll change the second one there, so I went from FIZZ to just 1Z, and if we run it, then you'll get this message, and you'll see the first 3 ran, the ones after that did not run. So you don't know if there's any other problems with it. You just know that, okay, I got a problem here and maybe more, right? So not particularly helpful. So that's tests. If you look at it as specifications, right, they tell you things. They tell you how things are supposed to work and what the system should do. So same idea, same input. But before jumping into things, the dev team's going to look at that and go, do we really understand what this is supposed to do? So this is what we've come up with, just rephrasing it ourselves, right? It's going to do the numbers from 1 to 100 unless you get these conditions, right? That seems reasonable. So then we can create the scenarios from that, right? There's different types here, right? Given an instance when it's called with a number, then you get this, or then you get that, or then you get fizz and buzz. Otherwise, you get the number. Okay, so now it's looking more like something logical, something that you can actually turn into code. And that's what we're going to do here. So, so this is the more stylized version. So, and here we've got some examples to see what this should do. And you can kind of see how this is turning into code. So we'll start. We'll take the text from that last screen and use that to fill in the describes and the test here. If you run this, it passes, which is frustrating, right? Because it doesn't do anything. And because it doesn't do anything, it doesn't throw an exception, and there's no assertion that it fails, so it passes. Fortunately, you can actually do this style with you put the test.todo, and now you get something useful that says, okay, nothing's broken, but I haven't actually run any tests yet, right? Sorry, back up that. When we run this, right, we start putting in our code here up at the top, right? Given an instance of this translator, and below that, it's okay, we're creating an instance of the translator. And this is where you can see we're starting to pair the code with the specification, right? So we've created the translator. We're going to start putting in the expect. So when it calls translate, it should return fizz, and we're saying expect translator.translate to be fizz. So you can see here, I've got a human readable description, and then below it, I've got machine executable description. And this is what makes it an executable specification, is because we're specifying what we want, and then we can also run it as a test. Okay, so if we go through this, and then we do this, right, we've created the translate, so that took care of the this previous error here, where okay, we put in the expect and we run it. It says, translator.translate's not a function, so we go ahead and add the translate. Once again, We're not having it do anything yet because we don't know what it's supposed to do at this point, right? It's just, it needs a translate method. So we're going to give it a translate method. We know it's taking a property, so we're going to pass that in. And OK says, OK, I expect you to get fizz from that. Well, the easiest way to do that is just go ahead and have it return fizz. Now, we know this is wrong because we know some of the requirements farther down. But at this point, if I check this in, everything is correct and accurate. It does what it says it's supposed to do, right? Because we don't have the other specifications yet. This is just the beginning. It's all passed, so you could go ahead and check it in. At this point, you should refactor, but there's nothing here that's duplicated, so there's no real refactoring necessary. So we'll do the second test, or the second example, and this is going to pass, and that's a problem, because you want to make sure that the test fails first, so that you know you don't have a problem with the test, right? Because we're building this, and it's failing, and it's failing, and it's failing, and then once we finally get the production code in there that make it work, the test passes, we know that the test is trustworthy because we've seen it work, right? It failed because this thing wasn't doing what it was supposed to, and as soon as we got the program to do what it is supposed to do, the test passes. Well, now it passed again, and we didn't do any changes. So the easiest way to fix this is to go here and just change fizz to fuzz. Now we're going to have two failures, right? And it failed because, once again, we expected that failure because we changed fizz to fuzz. So we expected it, and of course, it's doing it. So once again, we can trust what we're seeing. So if we fix it, everything passes, and we're good. You do the same thing with the rest of these, and you wind up with an output like this when you run it. But you can see, there's our specifications from the beginning, right? We ran it as a test, and you can see it's done all of these different types. It handles 3, it handles 5, it handles multiples of 3 and 5, and the things that aren't come back the way they're supposed to. So that's why specifications are a better idea than tests. First of all, it makes sense to use specifications. Just from a thinking about it, specs make more sense than tests. Having executable specs give us the best of both worlds. So that takes care of that. Yes, the Rosetta Stone. People have recently been talking about the great thing about TDD is it's like double entry bookkeeping, right? And if you're an accountant, or if you had to deal with accountants, you know what that is. Double entry bookkeeping is a way of tracking your money, right, in a business. For everything you have, whether you have assets or credits or debits, you record every transaction twice, 2 different places, right? One's for your assets, one's for your, I've forgotten the word for it, assets and liabilities, right? And if the numbers all add up at the end, you know all of your work is correct. And if they don't add up, then you know there's a problem. And so the whole idea with TDD is you have your test code and you have your production code, and if all the tests pass, you know it's good. That's like having your two books balanced, right? And if it doesn't, then you know you've got a problem. Okay, with what I'm showing you here, it's not double entry bookkeeping. It's more like this, the Rosetta Stone. Quick, in case you don't know, the Rosetta Stone basically was the clue for figuring out your Egyptian hieroglyphics. This is a stone that has the same message written 3 ways. The top part is hieroglyphics, which is a pictograph, right? So it's symbols, not alphabet. The middle piece is a form of Egyptian cursive writing, and the bottom is Greek, right? So when this was discovered in 17-something by the French, the people who lived in the town of Rosetta, in the city of Rosetta, they knew about it, but they weren't the French who came in and took over things and said, hey, this is cool. We can start figuring out Egyptian from this. So they were able to use the Greek to figure out what the Egyptian words were in the middle, and that helped them figure out what the pictographs were, because a pictograph could mean anything, right? It's like okay, it's a circle with some things. Is that the sun? What is that? We don't know. But so it worked for that. And so for this, we have 3 languages. We've got a human language, given an instance of fuzz translator. We've got a computer language, translator equals new FizzBuzz translator, and then we've got the production code down there. When a bug occurs, you can go to this and say, okay, are the business rules right? It should convert numbers that are multiples of 3 but not 5. Yeah, that's correct. Okay. Does the code that goes with this make sense? They expect translate 3 to be fizz. Yes, that makes sense. Okay, so the bug's got to be in the production code, right? Or no, that description is wrong. We changed that business rule 2 months ago. Why didn't you update it? I didn't know. Okay, so we'll change that. So now you update your business rule, then you modify the code below it to match the business rule, run it, see that it fails, and then fix the production code, right? So you don't have to go digging all over the place. Who here has had a bug that's taken more than an hour to fix, right? More than a day? Yeah. Question, how much of that time was spent fixing the bug and how much of that time was spent reproducing the bug? Most of it's reproducing the bug, right? Because once you find it, you can go, oh, well, here's the problem. Or you go, I don't understand that code. I need somebody else to help with this, right? But reproducing is the big deal. This, you don't have to find a way to reproduce it. This is telling you where to go. It's like, look over here. Your business requirement is wrong. Oh, the business requirement is right. It's got to be in the production code. Oh, and it's got to be in this area because this is the part that's being tested, right? So you come out with big benefits from this. Okay, so that's that piece. The 3 laws of TDD, who's heard of them, right? Robert C. Martin, also called Uncle Bob, has written a series of books, Clean Code, Clean Coder, right? Clean Architecture, Clean Craftsmanship. He's really into clean stuff. And it's good. He's done a lot of good things, but in 2005, which is like 3 years after that book, Test-Driven Development Explained, came out, he published his 3 laws of TDD. And they help a whole lot. A lot of us, for me particularly, I was trying to do it, and I was trying to figure out how to make it work and all, but it was really difficult to try and do things. But this helped a lot because it breaks things down into simple steps. And the first law is, you're not allowed to write any production code unless you've got a failing test. Okay, that forces you to do test first. Second is, you're only allowed to write enough test code to fail, and not running counts as failing. Right? So initially you said not compiling counts as failing. Which means you can only write enough code so that you're first mentioning a class or first mentioning a method, and you have to stop right there, which is what we were doing in that example. Right? I mentioned the FizzBuzz translator. Okay, I have to create that class. I mentioned the FizzBuzz translate method. Okay, I have to create that method. Right? So you put in just enough. So you create a class, but it has nothing in it. Right? Or you create the method, and it has to do a return because you're getting a value out of it. So you return null, or you return some screwy number. Right? And that way, it'll compile again, and you can keep writing your test code. So just enough. So and what this does is it says, oh, you can't just say, oh, I've got a failing test. I can start writing now, and start writing 2 hours worth of interesting stuff. So you write just enough to make it count. And then the third part is, oh, I'm sorry, this is it. You're only allowed enough to make that piece pass. So if it's failing because the class doesn't exist, create the class, create the method, put in fizz as the return value, right? So this is the 3 laws of TDD. And this, okay, the way he put it is, it locks you into a cycle of about 30 seconds where you have working code, you make some changes, and you have working code again. If at the end of that piece, if you get to writing the production code and you can't make it pass, or you've done something that you think should work and it causes something else to fail, worst case, you hit Control-Z a few times, you're back to working code, right? So it's a nice tight cycle, and you go, and it forces you to change your perspective, because when you're writing the test code, you're looking at things as a designer, you're looking at things as the end user, right? When you're implementing the production code, you're looking at it as the person who's making this stuff work. So you've got a completely different perspective of it. And this forces you to go back and forth, so you're more likely to see problems, because there are problems that you can see from this direction that you can't see from that direction, right? So these are the 3 laws of TDD, and they're really, really good, but they're also incomplete. And actually, I did a talk last year here called The 3 Laws of TDD Are Useful but Incomplete. And if you think about TDD, right, it's a 3-phase cycle. You write a failing test, you make it pass, or you refactor. Well, this doesn't say anything about refactoring, right? It's not in there. It should be in there. And in fact, in his most recent book, which came out at the beginning of this year, Uncle Bob talks about the 3 rules of TDD, and about 10 pages later, he says, oh, by the way, there's a 4th rule, refactor. We'll talk about that in a later chapter. I don't know that my talk had anything to do with that, because he was obviously working on that book prior to last year. But it's possible that somebody mentioned something about it and he went, okay, we can talk about that. And we just, right? So I'm going to take credit for that. Okay, so useful but incomplete because of that. And so I have my own rules because, I'm not wearing it right now, but I have a button that says, if at first you don't succeed, change the rules. Now that doesn't mean you can always do that, but sometimes. So I wanted to deal with two things. One is, how do you know what test to write? How do you know when you're done? And adding refactoring. So I start with this. You can only write an executable specification when you have an unmet requirement. That seems reasonable, right? If all your requirements are met, what are you writing code for? Right? So step two. This is where I use some of Bob's stuff, right? You can write just enough of the spec to fail, and not running counts as failing. You write just enough code to make that run. Okay, so that's, and then this is another key. When the spec is complete, and it's failing for the expected reason, right? As you're writing the code, it's going to fail for lots of crazy things. The method doesn't exist, or it's not returning what right? But you get to the point where your test is actually failing for the reason you expect it to fail. The system doesn't behave this way yet. Now you write the code to make that work, right? And then the last part is refactor. Make sure it's all easy to read and easy to understand. And what else? That's it. Okay, so that's beyond the 3 laws of TD. Living documentation. So the specs that you saw earlier, I don't know why it's flickering like that. The specs you saw earlier on the FizzBuzz thing, if that will hold still.
It's been doing that since yesterday.
Oh yeah, okay.
I think the projector, yeah.
That could be. Okay, well, hopefully nobody gets an epileptic fit from this, but if you can see up here, it says, given an instance of FizzBuzz translator, it should convert the numbers or multiples. This is the specification stuff. These are the things from the describe and the test phrases in the test code we wrote, the specification. You can publish this. This is actually from a web page. Publish this information. Show the business people, right? This is what I'm building. If you don't like it, you should say something. It's published, right? Also, notice the time here. Execution time, 0.336 seconds. That's the longest on this. I think that's the total on this. But 1 millisecond, 2 milliseconds. Okay, you can run these tests, type your stuff, hit go, and before you take a sip of coffee, they're done, right? So you get your feedback very quickly. You can see that it works. If it doesn't work, you get something like this, right? The top one is a failure. It tells you where, and if you click on it, it'll give you more information as to actually what happened. The one in the middle there, the purple one, that's one that just was a to-do, right? So it's not a failure, but it's something you need to look at because you're not done yet, right? So what that means is if you publish this, people don't have to ask you what the status is. Oh, I'm still working on that. See, it's red. Or I haven't started on that. It's purple. There's all the stuff that is finished, right? You don't have to bug me now. I can keep focused on my job, on my work instead of my status reporting work, right? So you get benefits for this stuff. So this is living documentation. I call it that because every time you run the test, it generates this. So if you get a new requirement, right, we need to modify this part down here so that instead of saying FizzBuzz, it should be FizzBaz. Okay, I change the specification. I make my changes in the code. When I run the tests, I now have accurate data up here as to what the system does. You don't have people walking in saying, okay, I'm the new guy on your team, I'm happy to go, can you tell me what it does? Well, the old ones wrote this and we had requirements, but they haven't been kept up to date, and so you kind of got to work your way through the code to figure it out, and Bob over here can step you through this really weird piece we call the heart of darkness. Don't touch stuff in there or you have to fix it forever, right? That becomes your code now because you've messed with it. Right? No, you have up-to-date specifications that tell you how the system is supposed to work. Right? That's the living documentation. Right? And anybody can read this. You can show it to the business people, technical people, your tech QA testers if you have them. Right? They'll be happy to see this kind of stuff because now they don't have to do that stuff. Right? Because you're already testing it locally. Or they can just borrow it. Okay, so that's living documentation. The last thing is extreme TDD. So I told you Kent Beck wrote this book called Test-Driven Development by Example. But he also wrote a book before that called Extreme Programming Explained. Anybody familiar with XP, Extreme Programming? Yeah. Okay. One of the main tenets of XP is, if something's good, do it all the time. So what I don't understand is why we have something really good here, and people just write unit tests with it. Extreme TD looks like this. Start with your unmet user requirement, write a failing UI test, which causes a failing API test, right? That becomes a requirement for my API. My API test says, okay, I need a service. My service says, okay, I need to have something actually do the work, right? I'm going to make that pass and refactor. And when I get enough of that working, my service passes. I can refactor that. And my service works, now my failing API test works, my failing UI test works. I have a complete feature. So use TDD to drive TDD at lower levels and lower levels. Some people, this is sometimes called top-down or outside-in, depending upon how you look at your model of data of your program. I don't know how they do it, but some people start off at the bottom and they start writing their unit tests. And they make a bunch of unit tests, and then they try to build things together. And the problem is, unlike Lego, which is going to work no matter how you click it together, if I build this wonderful piece of code and I want to now have it talk to something else, I'm probably going to wind up having to change the API because I wasn't thinking about what it should be, and now I have to make it work with something else, right? So I've got to modify either this piece or this piece so they can talk to each other, or I write some glue code in between, and that's kind of ugly. If you do it this way, what happens is you have something that was designed to work together. Each piece there was designed to work with the piece above it, right? And it's all there because you need it. So you don't have any dead code or unused code. So you wind up with a very efficient and effective way of producing this code. It's only what's supposed to be there, right? And you know it all works. And if something changes, you can change the specifications along the way. So that's that. Okay. That takes us to the summary. Let the computer do the grunt work, right? You can write a test and then just let the computer just do it and do it and do it. It doesn't care that it's run that same test 12 times in the last 10 minutes. It doesn't care that it's been 6 hours without a break. The computer's just fast and it's efficient and it's good at certain things. We should let it do those things because that lets us do what we like to do, writing code, right? And we do this by writing code. Don't write tests, write specifications and run them as tests. These are some really useful books. Kent's book, of course. This second book there, Growing Object-Oriented Software Guided by Tests, is called a Goose book because it's such a long title. But it'll walk you through the same thing, starting from one end all the way through writing the test to the other end of the code and back. This third book, Michael Feathers has wrote that, geez, it's probably 15 years ago. But it's still probably one of the best books on this. If you have code that doesn't have any tests and you need to start putting them in there, this is how to do it. It's like, I make the analogy of, if you have to go into an old abandoned mine and start trying to reactivate it, you want to put up some scaffolding so it doesn't collapse on you. This shows you how to put up the scaffolding and what to worry about. The last piece, specification by example, generally, when people think about that, they think about tools like Cucumber, where you have some text and you use some text matching to take that line of text and match it up with some code and then execute things like that. But that was the key to make me start thinking about, we can do specifications in our current test frameworks. You don't have to have a special one built for it. You can use the JUnit or the JS unit styles of programming frameworks and still get executable specifications. And that's it. Thank you. Do you guys have questions? Yes, sir.
So oftentimes our business requirements really change radically.
Yes.
And accelerated, like, things are A way and then B way the next day.
Mm-hmm.
So you said earlier to not essentially do anything until you know the entirety of the business requirements, but if it's accelerated or just kind of crazy,
yeah,
how would you address them?
Okay. What I actually said was, you need to understand what they want. Okay, you're not going to get the whole thing. right? So here's the deal. People say, oh, if I write tests and then I write my code and then the requirement changes, now I have to change this and this. That's extra work, it's harder to do. Okay, true, there is extra work there, but let's suppose you just have your production code and they change the business requirement. How do you know that you've actually implemented the new stuff and you haven't broken anything else if you don't have any automated tests? You don't, right? If you go in and modify the test that says, hey, go left here, and today it's go right here. Okay, I modify the test, this code fails, I make the changes here, this code passes, and I haven't broken anything else, okay? Because the other piece here is the specifications, right? If you notice in the code back there, there's nothing in those specifications that has anything to do with the implementation. Nothing in there says it should call this method, it should, right? This is the expected behavior, right? So if you have to change the implementation because, oh, we were using service A and now we're switching over to service B, right? And they do things differently. The test doesn't care how you do it. It just cares, am I getting the right answer, right? So you can change your implementation. You might not have to change the test code at all. But when it works, you'll know it's working, right? When that test code passes, you know you're actually meeting the business requirements. Stop that. I don't know why the white one makes it flicker more than this one does, but it seems to weird. But yeah, so if your business requirements are changing, that could be even more need for having these tests in place, because what happens when I change that requirement and it breaks a previous requirement, right? If you don't have any tests in place, you don't know. But if you have your tests in place, I make this change and suddenly this test over here is saying, hey, we've got a online sales stuff, and we say, oh, we're giving our top VIP customers 30% off anything, right? And they say, okay, we have some stuff we need to sell. We don't want to take a loss, so we'll cut it to this price, and that's going to be the special sale price. Okay, so one of our top guys wants to buy it, and he gets 30% off. You can't. No. This says that's the lowest price, but this says they get 30% off of anything. Okay, business guys, figure out what you want to do, right? And it's not like you have a problem in your code. It's, hey, there's a business issue here, right? So it can actually keep you from getting in trouble. So yeah, but yeah, when things are in flux, and here's the other thing, I am not a purist. There are times when TDD is not the right thing to do, right? If you don't know for sure what you're doing, you don't have any requirements that are stable, you can't write tests for it, right? It's not going to work. But on the other side, let's suppose you get a new library that you're supposed to use, right? Part of what you do is you play with it to see how it works and how can we call this thing, right? If you take what you're playing with and you write tests that say that, we need to do this, okay? And it all works. When a new version of that library comes out, can we use it? Hang on a sec. Let me run the test with the new version. Yes, we get the same right answers. We get the same answers that we're getting now. We should be good. Or no, it breaks when we call this method, or they change these parameters, or right? Because one of the tough things is, can we upgrade? I don't know. We can try it and see if it works. If you've got tests in place that do that manual testing for you, then you know right away, yes we can, no we can't. And if it's no we can't, you can send the reason to the people who made the changes and say, hey, did you know you have a breaking change here? And maybe they didn't, right? And they might fix it. So, yes, sir.
Yeah, I have a question. What your comment about the BDD and TDD?
Behavior, okay, yeah, so BDD is behavior-driven development, TDD is test-driven development.
Here, the description pretty...
This is BDD. But normally, when people think of behavior-driven development, they think of using tools like Cucumber or things like that, where, like I said, you have the business people write a text file that says, given this, when this occurs, this happens, right? The same things I've got here. Yeah. Two things that I've seen happen with this. One is the business people don't want to write that stuff. They don't care. It's like, so we wind up writing the text file for them, and then we have to maintain it, and it's slower because it has to do pattern matching, right? And all that stuff. It's much easier to do BDD like this than it is to use something like Cucumber. I'm sure other projects where you've got, it's a 3-month project or a 3-year project and first year is just figuring out what the requirements are. Maybe that works. But for day-to-day development, this is quote test-driven development, but I'm using specifications which come out of BDD, right? So, like I said, I'm not a purist. I find MUTs to be much more manageable, friendlier, all of that good stuff. So, yeah, I would call it BDD. And if you think about it, any test that you're writing really is about the behaviors. What is the code supposed to do, and is it doing it? To me, that's behavior. Now you can say, well, it's just, we're looking at results. We don't care about how it comes up with the results, and that's true. You don't care about the underlying implementation, the algorithm being used, right? But when I do this, I expect to see this happen. Okay, yes?
Another question. Do we need writing this test for all the classes? Because
okay.
for this class is function unity. Unity class.
This is a unit test, yeah.
But some page for us to the React.js, some component is for layout, some component is for test.
Oh, yeah.
So what do you test for that case?
Does it have behavior that you need to verify?
Just layout.
If you don't have any behavior, then what are you verifying, right? There's no need for a test on that. So in the Java world, there are data objects, right? It's all it does is it holds data. It's got getter setter methods, and you pass it to another thing or whatever. Same idea. There's no business logic there to test. And if the set fails, what can I do to fix it? I can report it to the guys who wrote the library, but I can't fix that. There's no business logic in there. If I write a class that says, okay, when you call set name, the name has to be unique, or the name has to have at least 3 letters, or I can test that logic, right? But if it's just getters and setters, there's nothing to test, right? On the other hand, that when you run your tests, right, those things should have test coverage, because otherwise you're not actually using those fields, right?
Exactly my dilemma. So some code just like this, for me, there's no sense to test it.
Right.
But if you don't test it, the code coverage will...
No, because if that's so the way code coverage tools, or at least the ones I'm familiar with work, is they say, okay, when I call this method, trace everything that it does, okay, and so that's what your code coverage is. It's what things got hit along the way, right? So if it's calling this other method and saying display itself, it got called, right? So you should get code coverage. If you're doing this stuff, you should wind up with, generally speaking, 90% plus code coverage without doing anything special, because the only reason you're writing the code is because you have a failing test, right? So you write the test, you write the code to make it pass. All that code that you just wrote got covered by that test. If you wrote extra code, right, you'll see that when you look at your code coverage and say, wait a minute, this else statement didn't get covered anywhere. Why did I write that else statement? Because I knew in my head I was going to need it, but I never did, right? And that would be the reason why you get the lack of code coverage. Yes, sir.
Just have a question more about the refactor step. I've always found that to be like the most ambiguous phase of the cycle. Like, I know that the test is failing, I know that I was passing, and I have refactoring. You were saying that like we're going to clean it up and whatnot, but my question is, do you have any heuristic rules basically to tell you I'm done refactoring at this point, so maybe we don't spend so much time manicuring code that doesn't need that?
Okay, so, great. His name escapes me right now, and he's somebody you all know. Martin Fowler. Martin Fowler wrote a book called Refactoring. And he's got patterns and stuff in there, but different types of refactorings. But generally speaking, for me, refactoring is about making the code easier to understand, easier to read, right? Because if you can read it and understand it, then you don't have to come ask me about it because it's all clear, right? In fact, one of my proudest moments was I was working at a company, and one of our junior developers came up and said, you know, I like working on your code because I always can tell what it's supposed to do, right? And that was the goal. And so I have another button that says, write your code as if whoever maintains it is a homicidal maniac who knows where you live, right? And I got that at a science fiction conference decades ago. And I went, yeah, that makes sense, right? If you write your code so that other people can look at it and go, I get it, then, right, they don't have to come to me to say, okay, translate, because this is all whatever, you know. So refactoring, the main things are, you want to get rid of duplication, right? Because if there's a bug in this code and it's duplicated over here, what are the odds you're going to find them? And maybe there's a third one, right? You have to remember to fix it in both places. If you take those and put them into one method and you call it from 2 different places, you only have to fix it once. And you can give it a cool name as opposed to, okay, I'm doing 37 lines of who knows what, right? Oh, this is the encryption section. Oh, that's why I couldn't figure it out. Okay, yeah. Okay, so encrypt, have it in one place. If there's a problem, I fix it one time, right? I don't have that same crazy stuff multiple places or slightly different versions that are supposed to do the same thing because somebody fixed one but not the other. If you look at refactoring, there's lots of suggestions for it. A lot of IDEs now have refactorings built in. But mostly it's give it a name that makes sense, right? And that's methods, classes, variables, right? Anything somebody's going to read, don't write SEC if it's section, right? Because sec could be seconds, could be anything that starts with SEC, right? It's a little more typing to start with, but it means somebody doesn't have to guess as to what you were talking about. One of the ugliest pieces of code I ever had to deal with had a method that had 4 variables in it. They were all labeled it. Capital I, capital T, lowercase I, lowercase, right? 4 different versions. You can't talk about that. I added it to it, and when I multiplied it, it was wrong. Which was wrong? It. Which it? Right? The people who wrote that were intending to be difficult to deal with, right? Computers don't care because they're just matching the numbers. But when you try to talk to somebody about it, if you can't discuss it with somebody else, maybe you should try to come up with a better name. Right? Anything else? Any other questions? Yes, sir.
Is this a specific tool that can consume test reports, or is this just a generated report from a specific testing library?
So I was using Jest. This is the Jest report. I think it's called Jest report. Jest-test-report, I think is what it's called, or report HTML. It's a standard library with Jest. There's another one called Jest-stare, which is similar, but this I like this one because it's easier to read, and you've got the time there, so you can see how long it took to do things. So yeah, but it's a standard library with Jest. Yeah. Yes, sir.
So in your FizzBuzz example, you were kind of going back and forth between you write the test, then you write the code and
Right.
the test, and then you write the next test.
Yes.
Right? And then in this living documentation thing here, you have the to-dos and things like that. So do you recommend writing out the specs first so that you have something like this, or do you recommend back and forth?
Part of it depends on what you want to do with it, right? So at the beginning, we said, okay, for FizzBuzz, these are the different specifications we had, right? So we took that list, and because it was a fairly short list, you could actually take that, just do the test.todos with the given when things, and put them up here, and they would all show purple until you actually started making them pass, right? And that way, your business guys could see it. If they use that, you might find it valuable. But don't bother doing that if it's just, if it makes you happy and lets you track it, that's good too, right? But if you're doing it because you should and you're not getting any value from it, don't bother with it. When you get to it, it'll be out there and people can see it. Yeah. So, any other questions? Yes, sir.
Did you use the React test library?
No, this was just for this. I didn't want to try and tie it to anything in particular, so I think just as kind of.
That's the React website.
Mm-hmm.
Recommend another library.
Yeah. Yeah, and this will work with pretty much any testing library in most languages, because a lot of them. So, geez, the original one was SUnit, I think, Smalltalk, and then JUnit got written on an airplane by 2 guys who were heading to a convention and became very popular. That was the Java unit testing framework, and then a lot of others got based off of that. And so there's generally speaking an X unit framework in any language, and they all have the same kind of structure to it. But yeah, and even if they don't, if you have a test name and it has to be a valid label, you can use camel case, so you can uppercase the words in there, or put what they call snake case. So you've got word underscore word underscore word underscore. Make it readable. That way people can look at it and go, oh, I mean, that's the name of the test. Given an instance of FizzBuzz Translator, it should convert numbers to right. It's like, people can look at that and go, oh, okay, I get what it's supposed to do, right? So here you go. Thanks for being here, and I hope you have a great con.